Okay, class, continuing on with this example, what you'll notice here is I said n equals 10, n equals 1,000, but the example that I worked was for n equals 5, so I want to apologize for that. So let's just add to our example n equals 5. So that's actually what I did. What I want you to do as exercise on your own is I want you to apply the same process for n equals 10, n equals 1,000, okay? So essentially my correction is this should read n equals 5. That's the example that we just ended up working, okay? So now we're going to move on to the topic of area, which is what this is a building block for, because you must understand summation notation in order to do the area problems. Okay, so let's just launch directly into an example. But before I do that, I want to discuss the definition of rectangle area. And that definition is simply area equals base times height, something you learned in your geometry class. So if we go to example 3 in the textbook, this is on page 257. We want to use 5 rectangles to find the approximation of area between x equals 0, x equal 2, and under the curve f of x equal minus x squared plus 5. Okay? So we know from previous classes that in order to draw this particular function, that what you're going to need to do is a table of values. Let's just pick the table of values to go from minus 1, this is the f of x column, 0, let's do plus 1, 2, 3. So that's our table of values. We're going to plug in each of these numbers into that formula. So if we do that, let's go ahead and let's do the easy one first. The easy one first will be plugging in 0 into that formula. Well, a negative 0 squared is just 0. 0 plus 5 is simply 5. A negative 1 squared plus 5 looks like this, negative 1 squared plus 5. Now this is a very common mistake. Many students might think this will be a positive one because negative is positive, but remember you have to follow the rules of PEMDAS. Exponents comes first. So if you evaluate the exponent first, that's going to be positive 1. 1 times 1 is 1. And then you have to bring over the negative, so that's going to be negative 1 plus 5, which equals 4. And you repeat the same process for the rest of the numbers, and you get for minus 1, you get a 4, for 2, you get a 1, and for 3, you get a negative 4. If you plot out your graph, let's do that over here. You plot your graph out, and let's put a negative 1 here. 1, 2, 3, 4, 5. And all we're going to do is just plot points. So when we plot points, I'm going to make the graph go from 1 to 5. 1, 2, 3, 4, 5. Very important that you label your axis, okay? And notice when I'm drawing this graph, I actually label the axis and draw the axis before I plot any points. So it's very important that you do that when you're working on this at home, okay? Always draw and label your graph before you plot any points. So let's go ahead and plot the first point. The first point is -1 and 4, so -1 and 4 is right here. 0 and 5 is right here. 1 and 4 is right here. Let's see, the next one is 2 and 1, that's right here. And 3 and -4, well, that's going to be down here somewhere, but we won't worry about that for now. So let's go ahead and connect the dots. So it's essentially an upside down parabola. That's the shape we're dealing with. This should be a little bit more curvy, but we'll just kind of bear with that. Okay, so we were supposed to use 5 rectangles to find the approximation of the area. So we've done several of these problems already, but like I said, today's flipped classroom is going to be more about some of the details. So I'm going to work through this part a little bit more quickly because you're familiar with this already. So let's go ahead and draw the rectangles underneath the curve. Since it's going to be 5 rectangles, between what? X equals 0. This is x equals 0, vertical line. X equal 2 is this vertical line. It's under the curve, f of x equal -x squared plus 5. That's the curve, so the area of interest, I'll use a different color just to avoid any confusion. So the area of interest is what I have here shaded in red. That's area of interest. So we need 5 rectangles, so we're going to use 5 rectangles. That means we have to divide this 5 different ways, so I'm going to try to make this 5 even divisions. We'll see how I do. 2, 3, that's okay. 1, 2, 3, 4, 5. So let's go ahead and draw the rectangles here. That's the first rectangle. That's the second one. That's the third one. That's the fourth one. That's the fifth one. So there you go. There are your 5 rectangles there. Okay? So what are we going to do? We're going to approximate the area that I have shaded in red by these green rectangles. So I'm not going to spend too much time on that because we've been doing that several times already. So let's go ahead and write this out. So we have, but before I do that, let's talk about the intervals. We have essentially 5 different intervals, and those intervals are defined by the following. Essentially 1/5 divided by 2. We're trying to divide 2 5 different ways, so it's 1/5 times 2. The first interval is going to be from 0 to 2/5. So this is 2/5. I know it's kind of hard to see. Try to write it a little bit clearer. That's 2/5. Of course, that's 0. The next interval is from 2/5 to 4/5. The next interval is from 4/5 to 6/5. The next interval is from 6/5 to 8/5. The next interval is from 8/5 to 10/5. So let's go ahead and label all these intervals on the graph here. So this is 4/5. This is 6/5. This is 8/5. And I'll draw an arrow there. That is 10/5. I know it's kind of small, but hopefully you can see that. Now notice that 10/5 is the same thing as 2, right? Because 10 divided by 5 is 2. So that's why I have 10/5 right there at the 2. All right, so hopefully that's clear to you. And so now what we're going to do is we're going to recognize that we're going to evaluate these at what I call the right endpoints, okay? So what I mean by right endpoints, I mean we're going to evaluate at this endpoint, evaluate what? The function at those endpoints, okay? At the right endpoints. So These red arrows are pointing to the right endpoints. That's what those red arrows are pointing to. Okay? And we can think of this as the set of the right endpoints as 2/5 times I. And if you don't believe that, let's go ahead and test it out, okay? Let's test this, let's test it out. So suppose I equals 1. Then 2/5 times 1 is 2/5. That's the first endpoint. Let's suppose I equals 2. Then 2/5 times 2 is 4/5. That's the second endpoint. So I just want to prove to you that 2/5 I is a shorthand way to represent the set of all endpoints that we're dealing with, okay? So I want you to kind of, pause at home as you're watching this. Just do a pause and make sure you've copied this down correctly. Make sure you've drawn this graph accurately on your paper, okay? Because it's very important to have this picture correct. So right now I want you to pause at home and just kind of look at everything that's on the board here and make sure you have everything copied down correctly, okay? So you can pause right now, and then I'll continue shortly. All right, so now that you've looked at that and verified that all the information is correct, I'm going to erase a lot of information here. And we're going to re-express this in summation notation that we discussed, I believe it was last week. So we're going to say the sum of the areas is given by the summation from I equals 1 to 5, f of 2I over 5 times 2 over 5. Okay? And if where does 2I over 5? That's the set of the right endpoints, remember? Because we said we're going to evaluate the function at the right endpoints. I said that earlier, okay? So by using the rules of function evaluation, if we substitute 2I over 5 into that function, so I'll do that over here, f of 2I over 5 equals, well, by substitution. Before I do this, let's just remember what substitution, what function evaluation is. It's just putting in whatever's in the parentheses into the function. So it actually tell me what f of 0 is. You would easily tell me that f of 0 is just minus 0 squared plus 5. So in the same thought process, f of 2I over 5 is just minus 2I over 5 squared plus 5. So let's go ahead and do that. So that's minus 2I over 5 squared plus 5. So we're going to put that over here. We're going to replace that, okay? So that's going to be summation. The answer we got here, that's the answer we got, correct? So that's the answer we got. For the answer of f of 2I over 5, we're going to do a replacement over here. So that's going to be minus 2I over 5 squared plus 5. And then I'm going to multiply that by 2 over 5. And again, we're still going from I equals 1 to 5. And if I essentially multiply this out, so let's go ahead and do that. So I'm going to get summation I equals 1 to 5. I'm going to get minus 2/5 times 4I squared over 25 plus 10 over 5. So you may ask, how did I get that? All I did was distribute the 2 over 5 to that term. I got that term. I distributed the 2 over 5 to 5 to get that term. So if we keep going, that's going to give us summation still from I equals 1 to 5. We're going to get minus 8I squared over 125 plus 10 over 5, which equals minus 8 over 125 I squared, I equals 1 to 5 plus summation I equals 1 to 5, 10 over 5. And if you recall, these are some of the same formulas that we dealt with in the last video. If you do the pattern recognition, you'll notice that this matches one of the formulas that we dealt with. It was summation dealing with I squared. This also matches the formula. It was summation of a constant. So hopefully, that's kind of familiar to you right now. So let's go ahead and continue over here because I'm running out of board space. So let's continue over here. So we're going to get let's just rewrite what we have. So using that substitution, from the formulas we had in the last video, minus 8 over 125. The substitution is going to give us n times n plus 1 times 2n plus 1 all over 6. Okay? And we're going to evaluate that at n equals 5. Let me just make a little separation here because I don't want you to confuse what I have down here. All right, so, and then we're going to add 10 over 5 times n. That's the second substitution to the formula that we talked about previously, at n equals 5. So again, I need you at this point of the video to pause, students. Pause at home. I'm going to keep going in the video, but at home I need you to pause. And I need you to go back to the previous video notes and notice that all I did was substitute. So I need you to take a few moments, look at your notes, and just realize that all I did was a substitution. It's very important you do that right now, that you pause the video right now, go back to the notes from the last video, and realize that all I did here was a substitution. There's a formula that dealt with I squared, I substituted it. There's a formula that dealt with a constant, I substituted it. It's very important you do that at home and pause the video, okay? So I'm going to let you do that right now. Okay, so we're back and we're going to essentially, since n equals 5, this is just notation that says everywhere you see an n, replace it with 5. So if we do that, we're going to get minus 8 over 125 times 5 times 11 over 6 plus 10 over 5 times 5, which is going to be minus, well, let's go ahead and do this one more time, minus 8 over 125 times 5 times 6 times 11, all over 6, plus 50 over 5. Okay? So yes, there should have been a 6 here. I apologize for that. There should have been a 6 there. All right? Let's keep going. Then we're going to get minus, after we cancel out some terms, okay, so that's going to be arithmetic, operations for you. That's going to be minus 8 over 25 times 11 plus 50 over 5, which is going to be minus, basically it's going to be 250 when it's all said and done over 25 minus 88 over 25, which is going to be 162 over 25. Okay, so I'm going to have to, when we have class on Monday, I'll review all this arithmetic. It seems complicated, but all this is arithmetic. But that's going to be our final answer. But I want to keep moving on because I don't want to get caught up in arithmetic right now. But we will cover, this is example 3 in your book. The reason I'm going over this is because essentially what the book did for you, and you're going to love this, what the book did was it basically said this was what we're evaluating, okay? So the book actually said, okay, we're going from here to here, and you're going to love this. It skipped all of this. and said, this is your final answer. So why am I doing this? Because you may be reading a book and you may not understand how the book from here got all the way to there. So I'm just basically filling in the blanks for you so you can follow the book a little bit better, okay? So that's one of the purposes for this flipped classroom, is to hopefully help you see some of the missing details in the book so that when we come to class we can kind of come with some level of understanding of the material, okay? Because sometimes, you know, the book unintentionally assumes that you know how to get from here to here because it is, you know, basic arithmetic, but it is somewhat complicated. All right, so, but let's move on. So what I want to talk to you about right now is this whole concept of, you know, the upper and lower sums, and I'm going to relate it back to this material, and we'll discuss more examples of this in class, but I at least want you to be familiar with notation, because for the flipped classroom, I want you to be focused on understanding some of the mathematical notation. Okay? So let's go ahead and discuss that right now. So we call these rectangles, the term for that would be inscribed rectangles. Okay? The term for that is inscribed rectangles. So just write that down in your notes. That says inscribed rectangles. And we actually call this a lower sum. Okay? So this represents what's called a lower sum, and we'll get into details of what that means in class. That's called a lower sum. And the general formula for a lower sum is the following. Let me make some more. I'll write it up here. So the general formula would be S in lowercase n equals summation from I equals 1 to n, that's an I, f lowercase m I delta x. This is on page 258 in your textbook. So let's go ahead and relate that formula to the picture, okay? Because it's very important you understand how that relates to the picture, okay? So the f of mi corresponds to the height of each of these rectangles. So you can think of this as your f of mi. And you can think of the delta x as the base of the rectangle. So each one of these intervals you can think of as a delta x. Okay, so that's the first thing I want to say. Because it's very important to be able to relate the formula to the picture because your mind thinks in pictures for the most part, okay? So if you don't get into the habit of relating what the formula is pictorially, it's going to be very hard to retain information. So I just want to reiterate that f of mi relates to the heights of the various rectangles. So this is an f of mi, this is an f of mi. It's basically the height of each of the rectangles. And the delta x in the formula, that's the delta x, that delta x relates to the bases of each of the rectangles. So that's what's called an upper sum. I'm sorry, a lower sum. That's called a lower sum. So in the last formula I'm going to deal with today, and we're going to pretty much wrap up the lecture after this, or wrap up the virtual lecture if you want to call it that. The next formula we're going to deal with is what's called a lower sum, sorry, upper sum. I'll just write down the board here for you. So the upper sum is given by this formula. So it's a capital S of n, and it's the summation from I equals 1 to n still, f capital Mi delta x okay? And so this also gives you an area, but we'll talk about this in class, but essentially it's going to be a different set of rectangles, and I'll tell you what I mean by that in actual class time, okay? But both of these formulas give you an approximation for the area. The area of what? The area of this area that's shaded in red here, the area under this curve. Okay? So what I want your takeaway to be, before we close out, is here in this example here, we only used 5 rectangles. So that gives us an approximation, but it's not a good approximation. Okay, so I'm finalizing everything, so I want you to kind of walk away with the big picture now. So in this example, we use 5 rectangles. And I showed you how to take these formulas and expand them out using some of the shortcuts from the last video. What I want you to understand is, in these examples, n was equal to 5. If you want to get a better approximation of area under this curve, you need to make n very large. Let's just say instead of 5, you make n 10,000. That's going to give you a great approximation of the area under the curve, okay? If you make n 10,000. This is why it's important to know how to use programming languages, because you don't want to, first of all, add things 10,000 times. Second of all, we want to be able to use shortcuts, because the shortcuts enable us to essentially determine what n of 10,000 is in just a few steps, as opposed to writing down 10,000 additions. So that's the conclusion. We'll talk more about the details in actual class time, but I want you to kind of have a big picture overview of where we're going before we cover this in class, because this material is fairly complicated, so I want to introduce you to it before we actually have class. So that concludes the lecture. Look forward to seeing you soon.